Next, we're gonna have a look at depth first search in action with graph data structure. And this is a top-down node collection. In this example, we're gonna see how we collect the information of the nodes from root to leaf, like this one, and see how this pattern of node collection is useful in solving real-life problems. Now our problem today is south path. Imagine at the root node, we have a factory that manufactures something, and all of the child nodes are distribution centers. We have level 1 distribution center, we have level 2 distribution center, and so on. The number in the node is the cost it takes to move the item from the parent node to that node. For example, this node is 3. That means to move the item from the parent node, which is the root node, to this node, it's gonna take 3 units of cost. Let's assume that's $3. And for the item to be distributed from the root node to this node, the cost gonna be the combined cost through all the distribution centers that the item has to travel through. So in this case, that's gonna be $13 for item to be distributed from the factory, go all the way down to this distribution center. So this tree that we see here represents the relationship between distribution centers and the cost of distributing the items. Our question today is, what is the minimum south path? That means if we want to distribute an item from the factory to the end distribution center, what is the cheapest cost? So to solve this problem, we can see that if we can collect the nodes from start to end and combine all the cost along that path, we can calculate the cost. And then if we can calculate all the cost, we will know which is the cheapest path. And by that logic, depth first search is a good algorithm to do it. And we're gonna do it top down with stack, data structure, and loop. So if we do a depth first search on this graph, we're gonna see 5 all possible cell paths. The first one is gonna be this one, 0, 6, 5, which is this one. The second one is gonna be 0, 6, 1, which is this one that we have here. And we're gonna have the third one, the fourth one, and the fifth one, which are all possible cell paths. And with our approach, the nodes collection pattern gonna be start to end, top down. We can do this with either loop or recursion. Now let's have a look at our self-path DFS implementation with stack data structure and while loop style. Here we're gonna prepare our path data. This is how a node look like. It's gonna have cost, it's gonna have an array of children. Each node also have a unique ID. Then we create our graph and add data into the graph. If we print our tree out, our tree is gonna look like this. Now let's comment it out for now. Now let's have a look at our DFS cell path implementation with while loop and stack data structure. We're gonna have a list of our scene nodes. And we initialize our stack with a given node. Always remember to use a proper stack data structure in real life. Here I'm using an array for quick implementation, and the pop and push operation of the array is not as efficient as the stack data structure. We're gonna have our path, which is the current path that we're traveling, and we're gonna have an array of paths, which is gonna contain all possible paths. With all the preparation done, let's start our while loop. When the stack is not empty, we're gonna print out the stack. This is just a helper function to print the stack beautifully. And first, we're gonna pop the stack. This logic right here is for adding the separator whenever we have new children of a node. This separator is gonna be very useful to keep track of our current path. Next, if we have never seen this node before, we're gonna process it. Otherwise, we're gonna ignore it totally. Now, if we have never seen this node, we acknowledge that we have seen it now. And these two values right here, it's just for helping keeping track of the separator and the current path. And with the current node, we're gonna add the children if we never seen it. And we're gonna also add the separator for the new children. This logic right here. Then we're gonna pop the current path whenever we as a leaf node. For example, if we are here at 5 and we want to explore the next possible path, we're gonna remove this 5 from the current path and then we're gonna add 1 to the current path. So we're gonna have a new path from 0, 6, 1. And we will also do the calculation of total cost when we reach a leaf node, that is 1 here. And that's what this logic is responsible for. After that, we return all possible paths. Then if we run our depth first search self-path algorithm, this is the results that we're gonna see. We're gonna have all possible paths along with the total cost of that path. And that is what we have right here in our photo. We have 5 paths, which are the all possible cell paths, and we have total cost of each path collected top down when we travel through every single node of this graph and we only visit each node one time. So the time complexity of our algorithm right here is O of n, with n is the total number of the nodes. Now remember, this is a DFS top down. We're collecting the node from top to bottom. In the next example, we're gonna see depth first search with a node collection of bottom up, which is we're gonna collect the node data from the bottom to the top. Next, with depth first search, example number 2, searching with graph, we're gonna have a look at the same example that we did previously, but this time with bottom up depth first search. To achieve this pattern, we will still searching the graph as deep as we can first. But the difference in this case is we're gonna explore the nodes in the bottom up order, like this picture that we have here. We're gonna explore this depth, but we only start processing the nodes from the leaf node, which is node 4 here. And that's why it's called bottom up. With depth first search bottom up, we go all the way down and start processing the nodes from the bottom, the leaf node, up. So it's an end to start node collection pattern. And just by the nature of the code stack and recursion, we can achieve this pattern by using recursion. We actually have seen this pattern a few times before today's tutorial. But this time, we're gonna officially name it. This pattern is depth first search, bottom up pattern. The most prominent and simple example of this pattern that we have seen is calculating factorial of a number. This is the code stack of calculating factorial of 3, and we vividly remember the code stack of this factorial function, that everything stack up and wait for factorial base case, which is factorial 1, and this is the recursion tree for factorial 3. So if we think about it, if 3 is our root and 1 is our base case, this is actually a depth first search. It's gonna go from root to leaf and then calculate up from there. And this pattern right here is actually what we're gonna use for our depth first search. Now remember, this is very important. There's nothing magical about this pattern. It's simply because of the way of how the computer is built that we have the code stack, and we're gonna use the like this nature of the code stack to implement our depth first search bottom up. So there's nothing genius or smart about using the code stack to do a depth first search bottom up. It's simply because we understand the fact of how the code stack works, and we realize that it's very suitable for depth first search algorithm. So we're gonna use it to implement depth first search bottom up. And with bottom up depth first search, the node collection pattern is gonna be from end to start, which is from the base case to the root. Now let's have a look at our implementation for depth first search bottom-up recursion style. We're gonna prepare the data with the same way we did last time. And this is our depth first search bottom-up implementation. You may realize by now, any algorithm with recursion usually have shorter code implementation compared with iterative implementation. That is because the code stack is gonna do a lot of work for us. And because of that, we don't have to write a lot of code. So our depth first search bottom-up function is gonna take in a root node, and right here we have a recursion function. This function is gonna take in that root node, and first we define our base cases. Or for our case here, it's just a base case because we only have one base case here. That's where we reach the leaf node. For example, we have the first base case here at node 4. If we hit our base case, we're gonna return the cost of that node. If we are not at the base case, which is the general case, if we are here at node number 5, we're gonna initialize an array of the costs. And this array length is equal to the number of the children of that node. Then for each of the children, we're gonna calculate the cost with the current node cost and the cost of the children. And then we're gonna return the minimum cost in the list. That's the case where we want to find the cheapest path. If we want to find the most expensive path, we can just replace it min to max. And if we run our algorithm, the cost we see is 7. Now the code is very simple, but let's have a look at what happened here. So when we call the function with the root node, it's gonna start here, and it's gonna go all the way down to the base case. And it's gonna return the first base case, which is 4 here. That's what we have here, leaf cost of 4. And when it comes to here, it's gonna plus 5 with all the children. And 5 only have one child. That's why we see that we only have 9 here. And when it comes back to this node, the root node has information of this branch. but it doesn't have information of this one, so it's gonna go all the way down to the base case, which is a leaf node here, and that's what we have here, and it's gonna go up from there with the same operation. So 1 plus 1 is 2, and this node only have one child, so that's what we see here, and it's gonna keep going up. 2 plus 2 is 4, and this node only have one child, and that's what we see here. And then it's come up to this node, but this node need information from both of the children, so it's gonna go all the way down to this branch, to the leaf node, and that's what we have from here. The cost of 10, then it's gonna go back up. 10 plus 0 is 10, and this node only have one child. That's what we see here, 10. So for this node of 3, we have the left branch has a value of 4, and the right branch has a value of 10. 4 plus 3 gonna be 7, and 10 plus 3 gonna be 13. Then we're gonna take the minimum cost in this array, and that's gonna be 7. So that's why we have number 7 here. So far for this branch and this branch from the root, we have 9 and 7, and our algorithm gonna run for this branch with that same logic, and it's gonna return 7, and that's what we have here. We have 9, 7, 7. All was calculated from the base case, the leaf node, up. And now to return to the root, we simply just pick the cheapest path, which is gonna be 7. It's either this path or this path. So that is how that first search with bottom-up solve problems. And the capability to do this is simply because of the nature of the code stack. So it's good to remember this case of depth first search bottom-up with recursion vividly, because this is nothing new and it always works this way. So you can reapply this pattern to your problem.